Next factor which affects the activity of enzyme is the hydrogen ion concentration or pH. Enzymes being proteins are polyelectrolytes or polyvalent ions highly sensitive to changes in the pH of the medium. Therefore, enzyme activity is highly pH dependent. At the same time, the pH maxima are different for different enzymes. The pH of the medium determines the net charge of the amino acid residues of the enzyme, especially that of the functional groups of the active center. Enzymes being proteins are polyelectrolytes or polyvalent ions highly sensitive to changes in the pH of the medium. Therefore, enzyme activity is highly pH dependent. At the same time, the pH maxima are different for different enzymes. The pH of the medium determines the net charge of the amino acid residues of the enzyme, especially that of the functional groups of the active center. This net charge in turn facilitates the binding and catalytic conversion of the substrate. The effect of pH on enzyme action is due to a combination of three factors, namely irreversible alteration of enzyme structure by extremes of pH. So, first of all, let's learn what is the effect of hydrogen ion concentration or pH on enzymes. Enzymes being proteins are polyelectrolytes or polyvalent ions highly sensitive to changes in the pH of the medium. Therefore, enzyme activity is highly pH dependent. At the same time, the pH maxima are different for different enzymes. The pH of the medium determines the net charge of the amino acid residues in the enzyme, especially that of the functional groups of the active center. This net charge in turn facilitates the binding and catalytic conversion of the substrate. The effect of pH on enzyme action is due to a combination of three factors, namely irreversible alteration of enzyme substrate by extremes of pH, effect on the ionization of the substrate, and effect on the enzyme substrate binding and the reactivity of the enzyme. There are three factors: irreversible alteration of enzyme structure by extremes of pH, effect on the ionization of the substrate, and effect on enzyme substrate binding and the reactivity of the enzyme. So, enzyme activity will be plotting in a y-axis and the pH of the medium will be on the x-axis. Then at the optimum pH, the maximum activity of the enzyme can be seen, and then it will be decreasing into 0. Unfavorable changes in the pH can affect the ionic character of the amino and carboxyl groups of the enzyme. This in turn abnormally alters its catalytic powers. Unfavorable changes in the pH can affect the ionic character of the amino and carboxyl groups of the enzyme. This in turn abnormally alters its catalytic powers. All enzymes are most active at an optimum pH range. This is because at optimum pH, all their functional groups attain maximum reactivity and the substrate become most preferred for their active groups. The effect of pH on enzyme action is due to a combination of three factors, namely irreversible alteration of enzyme structure by extremes of pH, effect on the ionization of the substrate, and effect on enzyme substrate binding and reactivity of the enzyme. Unfavorable changes in the pH can affect the ionic character of the amino and carboxyl groups of the enzyme. This in turn abnormally alters its catalytic powers. All enzymes are most active at an optimum pH range. This is because at optimum pH, all their functional groups attain maximum reactivity and the substrate become most preferred for their active groups. Any change in the pH value to either side results in the slowing down of enzyme action. Slowing down of enzyme action will be happening. The optimal pH value is different for different enzymes. However, for most cellular enzymes, it is close to the neutral value, the physiological pH value. An extremely high or low pH, extremely alkalinity or acidity, slowing down or stops enzyme action, or even destroys enzymes. Strong acids or bases can irreversibly inactivate enzymes by permanently changing their molecular conformation. Next is the effect of the concentration of enzyme. In addition to the physical conditions like temperature, pH, etc., there are two variables in enzyme action. They are enzyme concentration and substrate concentration. Changes in any one of them or both of them can alter the rate and velocity of enzyme action. The velocity of enzyme action is directly proportional to the enzyme concentration, provided the concentration of the substrate is high and other conditions are optimal. Thus, higher the number of enzyme molecules, faster the rate of the reaction catalyzed by them. If the enzyme is short of supply due to synthetic disturbances, etc., the reaction becomes very slow. This slow rate in turn becomes a limiting factor for the subsequent reactions in a metabolic pathway. So velocity of enzyme action will be plotted on the y-axis. Then we will be plotting the enzymatic concentration on the x-axis, and a line is drawn through the origin, cutting the two places equally. In addition to the physical conditions like temperature, pH, etc., there are two variables in enzyme action. They are enzyme concentration and substrate concentration. Changes in any one or both of them can alter the rate and velocity of enzyme action. The velocity of enzyme action is directly proportional to the enzyme concentration, providing the concentration of the substrate is high and other conditions are optimal. Thus, higher the number of enzyme molecules, faster the rate of the reaction catalyzed by them. If the enzyme is short in supply due to synthetic disturbances, the reactions become very slow. This slow rate in turn becomes a limiting factor for the consequent reactions in a metabolic pathway. So, what is the effect of substrate concentration? The velocity of enzyme action becomes directly proportional to the enzyme concentration when the substrate concentration is in large excess. But when the enzyme concentration remains the same, the effect of increasing substrate concentration will be different at different stages of the reaction. In such a state, the reaction will be diphasic. Initially, when the substrate concentration is low, the rate and velocity of enzyme action will be very slow. Initially, when the substrate concentration is low, the rate and velocity of enzyme action will be very low. This is because the active centers of all the enzyme molecules will not be saturated with substrate molecule. The steady increase in the substrate concentration correspondingly accelerates the K1 and K3 of the forward reaction and thereby enhances the rate and velocity. A steady increase in the substrate concentration correspondingly accelerates the K1 and K3 of the forward reaction and thereby enhances the rate and velocity of the enzyme action. This represents the first phase of the reaction. At this stage, the rate of enzyme action is directly proportional to the substrate concentration. So, the limiting maximum velocity will be here, and then the V is the maximum velocity of enzyme action. Then the reaction velocity of enzyme action will be there. So, first we will be plotting the substrate concentration on the x-axis, then the initial velocities of reaction on the y-axis. So, initial reaction rates at different substrate concentrations, S1, S2 and S3 will be there. So, substrate concentration. This is called first order kinetics or first order reaction. This continues until all the enzyme molecules get saturated with substrate. At this stage, the rate of K3 reaction and the velocity of enzyme action are limited or maximal. This stage is called Vmax, maximal velocity. It represents the second stage of the reaction. At this stage, the velocity of the reaction is independent of substrate concentration but proportional to the enzyme concentration. So, the formation and dissociation of the EP complex takes place at maximum velocity in dynamic equilibrium. Any further increase in substrate concentration will have no effect on the velocity of enzyme action. This is called zero order kinetics or zero order reaction. Thus, at optimum substrate concentration, the velocity of enzyme action exists in a steady state, free from substrate concentration. So first order reaction is depend on the substrate concentration. Second order reaction is depend on the enzyme concentration. Then the third one, that is the zero order kinetics, is depend on the no effect on the velocity of enzyme action. Okay, so kinetics of enzyme action, enzyme kinetics, we are going to learn about the enzyme kinetics. The kinetics of enzyme activity refers to the rate of enzyme catalyzed reactions affected by the three sets factors, namely the chemical nature and the relative concentrations of enzyme and substrate, the conditions for their interaction, and the environmental factors which influence enzyme action. Which are the three factors? The chemical nature and the relative concentrations of enzyme and substrate, the conditions for their interaction, the environmental factors which influence enzyme action. Otherwise stated, it is the molecular mechanistic nature of the factors affecting the rates of enzyme catalysis. The rate of an enzyme reaction is the amount of the substance converted into products per unit time. The kinetics of enzyme activity refers to the rate of enzyme catalytic activities reactions affected by three set factors, namely the chemical nature and the relative concentrations of enzyme and substrate, the conditions for their interaction, the chemical nature and the relative concentration of enzyme and substrate, the conditions for their interaction, the environmental factors which influence enzyme action. Otherwise stated, it is the molecular mechanistic nature of the factors affecting the rates of enzyme catalysis. The rate of an enzymatic reaction is the amount of the substrate converted into product per unit time. The rate of an enzyme reaction is the amount of the substrate converted into product per unit time. This in turn depends on environmental factors such as temperature and pH of the medium, influence the native or foreign materials, etc. The most fundamental property of enzyme is that they do not alter the thermodynamic properties of reactions, but alter only the kinetic properties which are related to the rate of reactions. Thus, enzyme kinetics is very important for a proper understanding of the rates of biochemical reactions. The most important variable of enzymes controlled reactions are substrate concentration and enzyme concentration. It is quite possible to alter the rate of an enzymatic reaction by changing the concentration of the substrate. The principles of enzyme reaction kinetics have been laid down by Michaelis and Mendel. According to them, the rate of an enzyme reaction is a measure of the catalytic activity of the enzyme, and it is simply referred to as the activity of the enzyme. Enzyme activity can be estimated either by a decrease in the amount of the substrate converted or by an increase in the concentration of the product formed per unit time. The rate of enzymatic reactions depends on substrate and enzyme. An enzyme reaction can be systematically represented by the equation E plus S gives ES, then EP and E plus P, K plus 1, K minus 1, K plus 2, K plus 3. These are the rates. Where K is the rate constant. Where K is the rate constant or velocity constant of the forward and reverse reactions. K is the rate constant or velocity constant of the forward and reverse reactions. Based on this equation, Briggs and Haldane derived a mathematical expression relating the reaction rate with substrate concentration. This is called Michaelis-Menten constant or Briggs-Haldane constant. So let's learn about the Michaelis-Menten constant, Michaelis-Menten constant, Michaelis-Menten hypothesis. Michaelis-Menten constant Km. K stands for constant and M stands for Michaelis. is the substrate concentration at which the velocity of an enzymatic reaction is half of its potential maximum. Half maximal velocity or half Vmax. At half Vmax of Km, half the number of enzyme molecules will be in the form of E, the others in the form of E2 enzyme substrate complex or enzyme product complex or both. Km value is different for different enzymes but constant for every enzyme. This means that the substrate concentration needed to saturate enzyme molecule is different for different enzymes. Km is significant in that this value is inversely proportional to the affinity of the enzyme for the substrate. So lower the value of Km, higher will be the affinity of an enzyme for its substrate. Conversely, the higher the Km value, the weaker the affinity between the enzyme and its substrate. For most enzymes, Km value is in the range of 10 raised to minus 5 to 10 raised to minus 2 moles. Km depends not on enzyme concentration but on substrate concentration. It is not depend on the enzyme concentration, it is depend on the substrate concentration. First order kinetics phase 1. All active sites are not occupied. Mixture of first order and zero order kinetics, and phase 3. All active sites are saturated. The overall velocity or rate of an enzyme reaction can be determined by applying the equation V is equal to Vmax of S by Km plus X. V is equal to Vmax concentration of S by Km plus concentration of S, where V is equal to velocity or rate of the reaction. Vmax is equal to limiting or maximal rate or velocity of a reaction at infinite substrate concentration. Substrate concentration in moles per liter of the solution. Substrate concentration of S. Km, the Michaelis-Menten constant in moles per liter of the solution. Substrate concentration at half maximal velocity. Now, let's learn what are the implications of Michaelis-Menten hypothesis. When the substrate concentration is lower than the Km value, the velocity of the reaction depends on the substrate and it will increase with an increase in substrate concentration. When the substrate concentration is higher than the Km value, the reaction velocity increases until it reaches a maximum velocity. When the substrate concentration is something which is very relevant. When the substrate concentration is higher than the Km value, when the substrate concentration is higher than the Km value, the reaction velocity, and the substrate concentration is higher than the Km value, the reaction velocity increases until it reaches a maximum velocity. When the substrate concentration is equal to Km value, the reaction velocity equal to half maximum velocity. Regulation of enzyme action. Enzymes are biochemical catalysts with controllable activity, so their action can be regulated positively or negatively, stimulated or inhibited by substances called enzyme regulators or enzyme modifiers. Positive regulators which accelerate or enhance enzyme actions are called enzyme activators, and negative regulators which slow down or stop enzyme action are called enzyme inhibitors. Regulation of enzyme action is a major mechanism which controls and coordinates metabolic process. Regulation of enzyme action is a major mechanism which controls and coordinates metabolic process. This regulation is affected by altering either the activity of the concentration of the enzyme. Regulation of enzyme action is of two main kinds, namely allosteric modulation and covalent modulation. Now let's learn what is allosteric modulation. This is the regulation of the functioning of allosteric enzymes by allosteric effectors, allosteric modulators, which can interact with the allosteric sites of the enzymes. Allosteric regulation is characteristic of a special group of enzymes having quaternary structure, active center, and one or more allosteric sites. Pyruvate kinase, aspartic transcarbamylase, etc. Active site is for the binding of the actual substrate, and allosteric sites are for the binding of allosteric regulators. These regulators include several metabolites, hormones, coenzymes, and metal ions. Binding of the modulator molecule at the allosteric site causes a change in the tertiary structure of the enzyme and alters the conformation of its active site. This in turn increases or decreases the affinity between the enzyme and the substrate and thereby activates or inhibits enzyme function. This is allosteric modulation of enzyme action. Positive modulation accelerates enzyme action and speeds up the catalytic conversion of the substrate. They are called allosteric activators. On the other hand, negative modulators retard catalytic conversion and so they are called allosteric inhibitors. The positive effect of activation is called positive cooperativity and the negative effect of inhibitors is called negative cooperativity. Activators and inhibitors may exhibit different degrees of specificity to their respective allosteric sites, as in the case of an active enzyme center. Active site correct conformation for substrate will be there, active enzyme will be there, allosteric activator site will be there. Inactive enzyme as active site incorrect conformation for substrate is happening and inhibitor site allosteric inhibition is happening. Schematic representation of allosteric enzyme activity. Then allosteric enzyme regulation is happening, like allosteric activator is there, inactive enzyme is there, substrate is there, allosteric inhibitor is there. So active enzyme and allosteric inhibitor will combine and inactive enzyme cannot bind with substrate. Where activation is happening, along with that inhibition is also happening. Some enzymes may have several allosteric sites. Some of the sites are specific to allosteric activators and others to allosteric inhibitors. Binding of the allosteric activator with the allosteric site causes favorable conformational changes in the active centers. These changes promote enzyme substrate complexing, decrease the Km or increase the Vmax. This in turn accelerates enzyme actions and brings about quick catalytic conversion of the substrate. On the other hand, binding of the allosteric inhibitor causes unfavorable conformational changes in the active site. This in turn prevents ES complexing, enzyme substrate complexing, increasing the Km or decreasing the Vmax and inhibiting the catalytic conversion of the substrate. Allosteric inhibition can be partially reversed by the addition of the substrate. Allosteric enzymes are highly responsive to metabolic changes, so they play a vital role in cellular metabolism. They take strategically important key positions in metabolic pathways and control the metabolic rate. They are called as key enzymes or rate limiting enzymes. Allosteric inhibitors are metabolically most important when the substrate concentration falls to a low level. In such situations, they exert control on enzyme action. When substrate concentration goes high, inhibitors become less active and activators become more active. This allosteric modulation of enzyme action appears to be very significant in regulating the metabolic rate and also in controlling and coordinating metabolic pathways. So now let's learn about the covalent modification. This is the modification of enzyme action either by the addition of a chemical group or atom to an enzyme molecule through covalent bonding or by the removal of chemical group or atom from an enzyme by cleaving a covalent bond. Phosphorylation, dephosphorylation, adenylation, deadenylation, etc. are processes commonly involved in covalent modification. Addition or deletion modifications activate some enzymes but inactivate some others. For example, glycogen synthase is active and glycogen phosphorylase is inactive in the phosphorylated form. This differentiated effect of covalent modification is important in regulating and balancing reciprocal pathways, making one of them more active and the other one less active at a time. An example is a synthesis of breakdown of glycogen. So now let's learn about the enzyme activation. Many enzymes are not active by themselves, so they do not function normally, nor do they function at all unless activated by some substances. Simple enzymes are activated in three ways. By structural changes, by the conversion of inorganic ions, mainly metallic ions, commonly called enzyme activators, by the action of kinases, like conjugated enzymes are activated by their cofactors. Activation of simple enzymes by structural changes. Activation of simple enzymes by structural changes involve the removal of a short peptide from an inactivated proenzyme. Activation of simple enzymes by structural changes involve the removal of a short peptide from an inactivated proenzyme, followed by some structural changes in the enzyme molecule. This transforms the inactive proenzyme to an active form, activation of trypsinogen to trypsin. This is the structural change. What is happening? Structural change is happening. Next is the activation of simple enzymes by inorganic ions. Activation of simple enzymes by inorganic ions. Inorganic ions stimulate enzyme action without serving as explicit participant in the reaction. Chloride ions activate salivary and pancreatic amylases. Pancreatic lipase is activated by bile salts, sodium and potassium. ATPase is by Na plus, K plus, Ca2 plus and Mg2 plus. Bivalent cations such as Mg2 plus, Fe2 plus, Zn2 plus, Mn2 plus, CO2 plus and Ni2 plus are also known to stimulate some enzymes. So, inorganic activators are of three major categories as follows. Activators which activate enzymes by entering into an obligatory interaction with free enzymes. Activators which activate enzymes by entering into an obligatory interaction with free enzymes before enzyme substrate complexing. For example, Zn2 plus or CO2 plus in carboxypeptidase and carbonic anhydrase, Mg2 plus or Mn2 plus in enolase, Mn2 plus in isocitric acid dehydrogenase. Here, activators which activate enzymes by entering into an obligatory interaction with free enzymes. That is what is happening here. And activators which activate enzymes by an obligatory interaction with free substrate. Activators which activate enzymes, they just activate the enzymes by an obligatory interaction with free substrate. Earlier, the inorganic activators are of three major kinds, namely activators which activate enzymes by entering into an obligatory interaction with free enzymes, activators which interact with the free substrates, for example Mg2 plus in reaction with nucleotide phosphatases. In this case, the substrate activator complex is a true reactant rather than free substrate. Third one is the activators which stabilize the specific conformation of the enzymes to ensure maximum catalytic efficiency. Activators which stabilize the specific conformation of the enzymes to ensure maximum catalytic efficiency. Activators which stabilize the specific conformation of the enzymes to ensure maximum catalytic efficiency. For example, monovalent cations such as Na plus, K plus, NH4 plus, etc. Enzyme activation by metallic ions is affected by a variety of mechanisms. In many cases, they facilitate the enzyme substrate binding by serving as bridge bonds. In some cases, they form part of a catalytic center. In rare instances, they link with free substrate and form a metallosubstrate complex, which is more advantageous for enzyme action. Next, activation of simple enzymes by kinases. Some enzymes, especially some proteolytic enzymes, are synthesized in an inactive form known as proenzymes or zymogens or enzyme precursors. They are activated by specific activating substances or enzymes called kinases. They are activated by kinases. For example, the gastric proenzyme pepsinogen is transformed to active pepsin by HCl. The pancreatic proenzyme trypsinogen is transferred into trypsin by the intestinal enzyme enterokinase. Enterokinase. Most of the enzymes involved in blood clotting are initially proenzymes thromboplastinogen, thrombogen, etc. They are activated by specific kinases. The activation of coenzyme seems to involve the removal of a short peptide unit followed by some structural changes in the molecule. So activation of conjugated enzymes by cofactors. Next stage is the activation of conjugated enzymes by cofactors. So what is happening here? Cofactors are actively involved in the accelerating the binding and catalytic conversion of the substrate. In some cases, they serve as bridge between the substrate and the active site of the enzyme. Often, substrate concentration may activate enzymes. The accumulation of the initial substrate of a metabolic chain activates an initial enzyme of that chain. This is called precursor activation. This in turn prevents the excessive accumulation of initial substrate. Substrate concentration may activate enzymes. The accumulation of the initial substrate of a metabolic chain activates an initial enzyme of that chain. This is called precursor activation. This in turn prevents the excessive accumulation of the initial substrate. Now let's move on to the next chapter, that is enzyme inhibition. Inhibition of enzyme action is the lowering of the rate of the biochemical reaction. It is a major mechanism which regulates cellular metabolism. The regulator substance which can slow down or even stop enzyme action are called enzyme inhibitors. They bind with specific enzymes reversibly or irreversibly and then adversely affect enzyme action. Their binding with enzyme reduces or removes the catalytic powers of enzymes, such as some drugs, antibiotics, toxins, nerve gases, etc. serve as enzyme inhibitors. For example, nerve gases are colorless, odorless, tasteless, and low volatile chemical warfare agents lethally toxic to man and other animals. Are organic derivatives of phosphoric acid like alkyl phosphatases, fluorophosphates, triphosphates, etc. rapidly absorbed through skin, eyes, lungs, etc. Sarin, sumen, tabun, etc. are examples. German nerve gases. These are toxic. So, first is the reversible and irreversible inhibition. Enzyme inhibition can be reversible or irreversible. In the former, the catalytic powers of the enzyme can be regained, but in the later, they got lost forever. Irreversible inhibition is most aptly termed irreversible inactivation. In reversible inhibition, the inhibitor binds with the functional group or other locations of the enzyme reversibly and non-covalently and forms an unstable enzyme inhibitor complex. This complex can dissociate easily, so the inhibitory effect is only transitory. In irreversible inhibition or inactivation, the inhibitor or inactivator binds with the functional group irreversibly and covalently and forms a stable enzyme inhibitor complex. This permanently inactivates the enzyme. This type of enzyme inhibitor is independent of substrate concentration. Poisons, antibiotics, insecticides, etc. are irreversible irreversible inhibitors. Which are they? Poison, antibiotics, and insecticides. There are different kinds of enzyme inhibitions, like based on the nature and mode of action of inhibition. Different kinds of enzyme inhibition can be recognized. The important ones are the competitive inhibition, non-competitive inhibition, uncompetitive inhibition, and substrate inhibition or product inhibition. First, let's learn about the competitive inhibition. This is the enzyme inhibition in which the inhibitor is a structural homology sufficiently similar to the real substrate to form an inhibitor-substrate complex. Yet, its difference from the substrate prevents the enzyme from acting on it catalytically. The inhibitor can reversibly bind with the active site of the enzyme and thereby prevent the enzyme-substrate complexing. It competes with the substrate for the same active site of an enzyme. If it wins the competition, it reversibly binds with the enzyme at or near the active site and forms an enzyme inhibitor complex. However, it will not get transformed to a product. at a time, an enzyme can combine either with a substrate or with an inhibitor and never with both. So either an enzyme substrate complex or an enzyme inhibitor complex would be formed and never an enzyme substrate inhibitor complex. Thus, competing inhibition appears to inhibit enzyme action by inhibiting enzyme substrate complexing. Since the competitive inhibitor and the substrate are sterically or structurally similar, competitive inhibition is also called isosteric inhibition. A classic example of competitive inhibition is the effect of malonic acid on succinic acid dehydrogenase, the enzyme that converts succinic acid into fumaric acid. The degree of competitive inhibition is directly proportional to the relative concentration of the inhibitor and also to its affinity for the enzyme, but it is inversely proportional to the concentration of the substrate and its affinity for the enzyme. So, competitive inhibition can be avoided or reversed by the addition of the substrate in large excess. The degree of competitive inhibition is directly proportional to the relative concentration of the inhibitor and also it is affinity for the enzyme, but it is inversely proportional to the concentration of the substrate and its affinity for the enzyme. So, competitive inhibition can be avoided or reversed by the addition of the substrate in large excess. Next one is the non-competitive inhibition. Now let's learn about the non-competitive inhibition. This is the enzyme inhibition in which the inhibitor prevents the catalytic conversion of the substrate to a product. So the inhibitor never blocks enzyme substrate complexing but only interferes with the conversion of the enzyme substrate complex to enzyme product complex. This in turn reduces the turnover number. On the whole, it appears that non-competitive inhibitors does not affect the Km but only decreases the V and reduces the K3. Heavy metals like Hg++, Mg++, Pb++, drugs, poisons, pesticides, etc. can act on non-competitive inhibitors. Thus, cyanide can inhibit cytochrome oxidase, fluoride can inhibit enolase. Non-competitive inhibitor is not structurally similar to the substrate, so it never competes with the substrate for binding with the active site of the enzyme. Non-competitive inhibitor is not structurally similar to the substrate, so it never competes with the substrate for binding with the active site of the enzyme, nor does it prevent enzyme substrate complexing. On the other hand, both the substrate and the inhibitor simultaneously bind with the enzyme, forming an enzyme substrate inhibitor complex. The non-competitive inhibitor will not usually bind with or modify the contact site. It binds either with the catalytic site or anywhere outside the active site. Binding occurs mostly through covalent bonding. Binding with the catalytic site directly blocks enzyme catalysis. Binding outside the active site induces conformational changes in the enzyme molecule. This in turn affects the structure of the catalytic site and prevents its action with substrate. The rate of non-competitive inhibition is directly proportional to the concentration of the inhibitor and its affinity for the enzyme. So here we are drawing an enzyme with altered form. PSI complex is formed. Non-functional catalytic site with altered conformation is here. Non-functional catalytic site with altered conformation, substrate will be there. So non-competitive inhibitor, unchanged substrate. Substrate is not transforming to product. Okay, so that is what happening in the non-competitive inhibition. Enzyme with altered form, ESI complex is there. Non-functional catalytic site with altered conformation substrate. Because of the formation of enzyme substrate inhibitor complex, the active site changes its conformation. So due to that, there won't be any conversion of enzyme product complex. There won't be any product forming.